What's going on, everyone? So today we're going to talk about refraction because apparently this is a controversial topic somehow. There are some flat earthers that like to have this argument of you can't use standard refraction, which is what land surveyors use, and it is their job, their day-to-day life, and they use standard refraction. These people like to say you can't use it because the refraction, the atmosphere is different in Ohio, Hawaii, Phoenix, Chicago, New York, the Congo jungle, all that stuff. So what we're going to do is do the math for two different locations, Phoenix and Chicago, and two entirely different weather patterns, July 1st and January 1st. And that way we'll get a mix of data to see why standard refraction is acceptable. So on Walter Bislin's website, it talks all about refraction here. If we scroll down, there is a formula to calculate the refraction coefficient. And this is the coefficient that you use to plug into the calculator. What we're going to use as our kind of example observation is the Joshua Nowicki Chicago one. This is one that flat earthers love to use, but the fun thing that they forget to do is, as you look, the photographer himself says, Chicago taken after sunset from the top of the dunes at Warren Dunes. And it's about 52 miles away. I measured it, it was 53 miles, but he says top of the dunes. Now if we go to Warren Dunes page here, the tallest of the dunes is 240 feet above Lake Michigan. Flat earthers seem to leave out that he is at elevation. But because we don't know what dune he was on, we're just going to do 200 feet because it's a nice round number. Now I did this by hand a year and a half ago or so, and that was a struggle for me. So we're going to use ChatGPT. I screenshot the formula, plugged it in there. I have this whole thing, observer height, target distance, compute what that is from the geometry. These I asked ChatGPT before to give me, and we're gonna go one city at a time. Okay, so it converted a few things. And what we're gonna do is grab the data from dateandtime.com. So this is Chicago, this is January of 2025, January 1st, and we're just gonna grab the time closest to noon with every one of these observations. So it might be off by a few minutes. So we're plugging this in. I just typed in temperature, wind, humidity, and pressure so that ChatGPT doesn't have to figure it out. And I spelled pressure wrong because I just can't type for crap. Okay, so here's all the math it did for us. We'll scroll through it, and it gave us the coefficient of 0.19. So we'll plug that into our first spot here, 200-foot observer, 52. We'll do 53 miles. Willis Tower is 1,450 feet, 0.19. And now what we'll do is grab Phoenix's weather, January 1st, 2025. Scroll down here to as close to noon as possible. We've got our temperature here at 64 degrees, midday in winter. That's amazing. Humidity 26%, and the pressure 30.12. And while this is calculating this, so why I use the Joshua Nowicki observation is because flat earthers use it, and I kept it consistent saying, well, what if we could make this same observation in Phoenix with Phoenix climate, like we had a flat somewhere. We're a mountainous region, but what if we had a very flat section? Okay, so Phoenix, we've got a coefficient of 0.15. Well, let's go here, 0.15. So now, let's see, with Chicago, our standard observation, we took this observation January 1st, 2025, the hidden height of Willis Tower should be 615 feet. Now in Phoenix, if we did this, the hidden height of Willis Tower should be 663 feet. Now that's a difference of 48.1 feet. So with this observation, that would be seeing a 4-story difference. That is it. So when we do this math, the 4.5-story distance about the difference. So when we do the math for this absurdly long observation, and we use the difference in actual refraction versus standard refraction, we don't have that much of a difference with this absurdly long 53-mile observation. Like I said, it's a 48.1 foot difference. But that was winter. That might be different. So let's check the summer. We're going to do July this time. July 2025. Same thing. We're going to go, this is Chicago. We're going to go as close to noon as we can. So we plugged in that data. We'll let it do its thing. Grab that number quickly. It's giving it to us as a table here. So I'm just going to grab Phoenix in July. Okay, so here we've got Chicago and Phoenix. So 0.16 and 0.13. Go Chicago here, 0.16. Phoenix here, 0.13. So with Phoenix, with our 0.13 refraction, we've got 687.9 feet hidden. In Chicago, with our 0.16, we have 651.6 feet hidden. So that's only a difference of 36.3 feet. Again, that's like 4 stories. So in this picture, we would be seeing 4 floors difference in the different refraction of Phoenix and Chicago on July 1st in the summer when it's kind of hot. But the last thing that we're actually going to do is, let's say this is a realistic observation, one that a flat earther, globe, or a land surveyor could make. 6-foot observer, 15 miles. We're looking at a target 200 feet tall. In Phoenix, we're going to have a hidden height of 77.04 feet. In Chicago, for this same observation, 6 feet tall, 15 miles, 200 foot target, we're only going to have 80.57 feet. That's only 3.5 feet, 3.53 feet difference between Phoenix's weather in the summer and Chicago's weather in the summer at a 15-mile observation. So the next time you hear about somebody complaining about standard refraction or using a standardized refraction, just remember, real professionals use it. Surveyors, engineers, bridge builders, highway planners, anyone who needs precision. Or you can listen to the guy on TikTok who's confidently wrong and refuses to do the math. But at 15 miles between Chicago and Phoenix, it is a 3.5 foot hidden difference. That's why we can use a standard number, a standardized number, because it's not a huge deal, especially at those distances. Thank you for coming to my TED Talk on how standard refraction is perfectly fine, and when you do all of the math, you can see that the change is so minuscule that realistically, looking at a picture like this, you're not going to tell me plus or minus 3 or 4 floors.